Okay, my name is Jingyu Park in HPMI. So today I introduce about atomic force microscope in the HPMI. So different size of material exists in the nature, and from macro to micro to nanoscale. So macro to micro scale object you can see either eye or microscope, optical microscope. But in nanoscale materials you cannot see it in optical microscope. For that materials you have to use different tools, either electron microscope or atomic force microscope. So this is a simple comparison between different microscopic techniques. So optical microscope, you can easily use it, but the size limited to the typical around 200 nanometer depending on the wavelength you use. And electron microscope, you can see small object easily, but it's more expensive and needs some more vacuum, and typically those information you can get is typical 2D information. So AFM can be operated either ambient or vacuum or different environment can be operated, and it gives you 3D information. So you have 2D information and also height information as well. And also if you see the resolution wise, XY resolution is 0.1 nanometer range and G resolution is 0.01 nanometer. So it's high resolution for G. So for the AFM, you have to start with the STM. It's the scanning tunneling microscope that's developed early 1980s, and they received Nobel Prize in 1986. But that's basically based on the tunneling current between two materials. One is the metal tip, and another one is a sample. And there's a tunneling current between them, and then based on the distance, the tunneling current is different. So then you scan the tip on the sample surface, and depending on distance, the tunneling current is different. So in other words, if you maintain same tunneling current, that means you have same distance between tip and sample. So then when you scan the tip on the sample surface, so you maintain the same tunneling current, that means, okay, you have to move the tip up or down, maintain the same distance. And based on this tip movement, you have some idea about the surface morphology. That's the scanning tunneling microscope. So atomic force microscope, that's similar, but they use a force between atom and atom. So the graph you saw in right side is based on the Reynolds-Jones potential between two atoms, and they are very close. There's some repulsive force. If there's some distance, there's some attractive force. So unlike the STM, they use a tunneling current. AFM, they use the same force between two materials. So then you maintain the same force between tip and sample. Okay, you scan the tip on the sample surface, and then to maintain the same force between tip and sample, you move up and down the tip. And based on that, you have some idea about the surface morphology. That's the concept for AFM. So now you see the simple structure of the AFM. So then it consists of the AFM base, and then in the middle is a piezoelectric tube. They move the sample up and down, just a precise control based on the response. And then top part is a head. If you see the head, there's some tip holder. In the right side, you can see some tip holder, and then some small silicon tip is mounted in this tip holder. So if you see the SEM image of the tip holder, typically it's small, and if you see the tip end, that's really sharp, and tip radius is less than 10 nanometers. And depending on the imaging mode, you can get different images, where we typically use either contact mode or tapping mode for the imaging. Or if you want to use some electrostatic force or magnetic force, you have to use a different mode, and then you can get some idea about that, either magnetic force imaging or electrostatic force imaging on the sample surface. Not only for the imaging, so it can also have other physical properties can be measured. Either you can measure electrical properties, and if you have the thermocouple pattern on the AFM tip, you can get the thermal properties, and also it works as a spring, and you can get some idea about the mechanical properties of materials and optical properties, and then you can also make some patterns in nanometer scale as well. So there's other application other than just a simple imaging. I show you the simple procedure for the sample preparation and then the imaging for the AFM. We use some carbon suspension, and then we drop it on the silicon wafer. Silicon wafer is really flat surface. We drop it and blow dry, and attach it to the small metal stub with the double-sided tape. I attached it, and I mounted to the AFM with this magnetic top head. So then this stick to the surface of the piezoelectric tube, and I mount the head part with tip head, and then fix it with some spring. After that, I go to the software and then see the optical microscope image real time, and I lowering the microscope. If I lowering the microscope as going down, you can see the AFM cantilever is focused. If I lowering a bit more, you can see the sample surface. Then in the software, I just decide the scan size and scan rate, and just press engage it, and AFMT will engage the sample surface. It will take less than a minute depending on your distance from tip and sample. So after approaching the surface, if it engages the surface, it starts to scan. So you can hear some sound, and then they start to scan. So you can see something shows up in the screen, and there's several different images shows up, and you can see some line profile. Some line profile is the tip is scanned to the surface, and then you can see something shows up. That's some images of your sample image, either nanotube or other impurities can be shows up. And now you can see some images shows up in here from top to bottom. They scan top to bottom, and it depends on your scan rate and scan speed. But typically we set around 8 minutes for one scan images. You can see it's gradually scan from top to bottom. The image shows up, and after finish it, okay, you can see the image shows up in here. Okay, now they finish the scan. Then you can select some area you want to zoom in, and you can move it, and you just zoom in, and then execute it. They start to scan it again, and then capture the image again. So you can just going on and on with different areas if you want.